All right. Welcome, everyone, both those of you in person and those of you online. Our colloquium speaker today is Gina Panopoulou, who's a postdoc here. And I have the pleasure of introducing Gina. So Gina comes to us originally from Crete, where she describes herself on her website, staring up at the night sky and discovering the joy of astronomy. And she attended the University of Crete, where she got her PhD in 2017, working with Kostas Tassis on the structure of magnetic fields in molecular clouds, a topic she's continued to be interested in. And it's worth noting for her PhD, she won the IAU PhD prize the same year. She came to the US to work with Tony and others here. And then in 2019, received a Hubble Fellowship and chose to stay at Caltech. We were fortunate enough that she started working with our group and other groups as well on both the theory and observational sides. So Gina's an observer who's worked on a range of problems in understanding the ISM, with a special interest in things like magnetic fields in our galaxy. And she's an expert in using polarization data. I'm sure we'll hear something about polarization in her talk. And she's written a number of high impact papers on topics ranging from sort of 3D structure of the ISM, magnetic fields, ISM dust, the kinematics of molecular clouds and turbulence, and what I regard as the really the definitive papers on a topic that we've been debating for a decade since Herschel about the structure of filaments in the ISM and whether there's sort of universal structure or not in them. And she's had a growing web of collaborators in the last few years, including not just folks on campus and ourselves, but also a number of people at JPL that she's begun working with and talking to on a variety of topics and branching out into things in our discussions like cosmic rays and a number of other galaxy formation questions. On a more personal note, I have to say, when Gina sort of started working with our group and asked me if I would be her sponsor for her Hubble Fellowship, I sort of said, you know, what am I going to do for this observer being a theorist? And I still don't know the answer to that question. I don't know if I've actually provided anything useful for Gina as a mentor, but I can say I've been fantastically lucky in what she's brought to our group. Gina's, for one, a fantastic mentor who's done a really amazing job working with students. Right now, Sam Panada, for example, Gina's really a co-mentor on his project and involved in a number of other projects. And she's a font of project ideas. I keep my project ideas notebook, and there's about 25 that Gina came up with that I think are good projects. I just don't have 25 students or the bandwidth to support that many. So if you haven't already had a chance to talk to her, I really would encourage you. We're fortunate enough to have her here, so you can track her down your convenience after this talk and you know, talk to her about different ideas. And I guarantee you she'll give you interesting ideas about how we might connect them to different topics or come up with new ways to explore different observational implications and tests. So thank you very much, Gina.
Thanks, Bill. Thanks a lot. Hi, everyone. Good to see you all. So let me first do the full screen thing. Maybe that will work. It works. All right. So before I start, let me prime you a little bit. So when Jim told me yesterday, hey, can you do the colloquium? I was like, okay. I was fortunately preparing my slides for a job interview I have next week. Now, the audience for that talk is going to be a little bit different than today's audience. So let me prepare you by saying, let's do a mental exercise. Let's think that all day long, you have only been thinking about bacteria or about graph theory. Okay. So now that we're all prepared, I can give this talk. So what I'll talk about today is something apart from gravity, Colin. I will talk about the big question in astrophysics, how galaxies evolve. And so over the past century or so, half a century, let's not be overestimating things, cosmology and astrophysics have given us this basis of understanding about how the universe evolves. So we know that the universe started from an infinitely small, infinitely dense state, and it grew exponentially, cooling as it went, and there were subatomic particles that formed, and protons combined with electrons, and the universe was transparent. And photons traveled to us from that time, 400,000 years after the Big Bang, and we can study these photons to learn about the universe as a whole. And of course, after that, stars and galaxies and other things formed, and we come to the present day. So by studying the tiny fluctuations in the light that came from the Big Bang, this relic radiation, cosmologists have understood what the basic makeup of the universe is. We know that it's made up of things that we don't understand. There is dark energy, this mysterious anti-gravity force that expands the universe at an accelerating rate at late times. There is dark matter that is a particle that interacts gravitationally, and that's about what we know. And there's ordinary matter, which makes up stars and humans and planets. And so in order to learn about the universe and its evolution, we can code up the fundamental laws that describe how these components of the universe work. And we can put that in a computer simulation and look at a movie of what the universe we think did over its time. So I have a movie to show here. And so technical issues with Linux, it's kind of hard to sort of embed movies in the presentation. We don't care about this. We'll just jump straight to watch the movie, which is shown here. And what you're going to see is on the left, the distribution of dark matter. Hopefully you can see this a little bit better. And as time goes by, gravity pulls structures in the dark matter distribution to smaller and smaller scales. Denser and denser structures form. And on the right, you're also starting to see the normal matter, actually the gas temperature, the temperature of the gas that makes up normal matter. And so the normal matter is a good tracer of the distribution of the overall matter, of the dark matter. So let's make a still of this image here, of this movie, and look at the things in a little bit more detail. So this is the still shot. The left side of this image is showing you the dark matter distribution. The right side of this image is showing you the normal matter distribution, the density field. So this is primarily hydrogen gas, as we all know. And this is a zoom in on one of those density peaks that we saw in the movie. So overall, if you were to correlate these two parts of the image, you'd find a good match. Because on large scales, normal matter is a good tracer of the dark matter. But if you look into the details, if you zoom in on smaller scales, you find that normal matter isn't such a great tracer of the dark matter distribution. You can see the dark matter is a little bit clumpier, normal matter is a little bit more diffuse. And so the reason for this, of course, is that dark matter acts only gravitationally, and normal matter also interacts via the electromagnetic and nuclear forces. And so in order to be able to understand the entirety of the universe, we need to rely on normal matter, the only matter that interacts with light, the only matter we can see. And so we really need to understand this matter well enough to be able to map from normal matter into dark matter. And it turns out that the details of how normal matter works aren't as clear as we would like. So what I'm showing you here is the same kind of simulation of large-scale structure in the universe. On the left, the simulation has been run with one type of model for what the baryons, what the normal matter is doing. And on the right, you're seeing the same kind of simulation, just different prescription for how normal matter behaves. And you can see, okay, on large scales, they sort of agree, but there are important differences in the details. And so the details actually are different because of things that happen on scales smaller than a pixel in this image, because of things that happen inside of galaxies and their surroundings that we don't understand. So that's where one of the basic questions in astrophysics comes in. That's where we want to understand how galaxies evolve. And this big question of how galaxies evolve can be broken up into a series of smaller questions, like how galaxies form stars, when and where do these massive stars explode, how do black holes form inside of galaxies, and how do the exploding stars and black holes interact with the surrounding medium. So in order to make progress, let's go in and look at this part of the universe that is galaxies, the building block of the universe. Galaxies, of course, are assemblies of dark matter and stars and gas. And the latter two we can see. And they're the sites where stars form and where black holes form and where everything that we know and love exists. And so the events that happen to create this uncertainty in the large-scale properties of the universe, of the normal matter, are associated with, for example, explosive events that happen within galaxies. For example, supernovae and black holes. So stars explode and create outflows of gas in the surrounding medium, and black holes power very quickly moving jets, and these emit material at distances much, much larger than the scale of an individual galaxy. Now, these kinds of processes have received a lot of attention because we wanted to understand how they affect the evolution of galaxies. We still have a long way to go, but we're at the point where there exists a lot of observational constraints, and there exists a lot of different theories that are starting to converge on what order of magnitude behavior we should expect for these kinds of processes. Now, on the other hand, there are some components of galaxies that we don't really understand that well. They haven't been studied as much, probably because they were harder to measure and harder to model. But now we're coming to a point in time where we really need to start modeling these two components. And the components that I'm talking about are magnetic fields and cosmic rays. So we know the universe is partially ionized. If you have charges that are moving, hopefully this will stabilize. Okay, if you have charges that are moving, there will be magnetic fields. And these magnetic fields will affect the motion of the gas in turn. And on the other hand, these explosive events like supernovae that I talked about, they emit very, very energetic subatomic particles. These particles travel at the speed of light, and they also add changes in how we understand the behavior of galaxies. So we know about these two components from examples here on Earth. If we look at the sun and its wind, the sun emits relativistic particles. These get trapped when they encounter the Earth's magnetic field, and they are channeled to the poles of the Earth, and that's how you get these spectacular displays of northern lights. Now, in detail, in the context of galaxies, the way that these two components work is primarily to oppose gravity. So if you try to use gravity to pull magnetic field lines together, these will counteract that force in their attempt to remain straight and parallel. And on the other hand, these relativistic particles, the cosmic rays, act as an extra fluid and add extra pressure through collisions with the gas particles. Cosmic rays are charged particles, so they're coupled to the magnetic field. And if you want to understand either of them, you have to jointly model them. So just to give you a little bit of a more quantitative sense to what I'm saying, what are the effects that cosmic rays can have? So Jacob Shen, who's a grad student here, was kind enough to share these snapshots from his simulations. And what Jacob has been working on is to model different theoretical ideas about how dark matter behaves. On the left, you're seeing a simulation of a galaxy run with cold dark matter. And this central panel shows you the same simulation, same galaxy, but now you're using a different model that's called dissipative dark matter. And you can see that the distribution of the gas in these two galaxies is very different. And that could be, in principle, a way to discriminate between different dark matter particles that have been proposed. But the problem is that normal matter doesn't behave in ways that we understand. So the same kind of qualitative changes can also happen in galaxies. For example, if you add cosmic rays, which is the panel on the far right, compared to if you don't add them, which is the panel just to the left of the far right image. So let me quantify the statement a little bit more. If you add cosmic rays to the simulation of this galaxy, it does change large-scale properties of the galaxy. And fellow collaborators showed that, for example, the star formation rate as a function of cosmic time changes. And it can change by an order of magnitude. The run without cosmic rays is the red line. The run with cosmic rays is the blue line. And you can see a suppression in the end result of the star formation rate when you add cosmic rays, this extra pressure. The main uncertainties that come from understanding cosmic rays come from the properties of the magnetic field. Because cosmic rays are charged particles, if you put them in a magnetic field and kick them, well, they have their own velocity, they will follow trajectories like the one shown in this slide. And if the magnetic field lines start to wander, so will the particles. And the main uncertainty in understanding how cosmic rays react and how they affect galactic evolution comes from our uncertainty on the properties of the magnetic field. So if we knew the properties of the magnetic field, then we could solve two problems with one go. We could know what the properties of cosmic rays are and how they affect galaxies as a whole. Now, the problem is, as some of you might know, that we don't know magnetic field in galaxies that well. In fact, we don't know them very well in our galaxy, which is the most well-studied system. So this shows you three models that exist for the Milky Way's magnetic field, where an observer placed on top of the galactic center, and we're looking straight down, face on. The colors show you the strength of the magnetic field. The vectors show you locally where the magnetic field is pointing. And you can see by eye there are qualitative differences between these models. Now, the reason why we're stuck with these models is because we've been using data that have a fundamental limitation. The limitation comes from the fact that we live inside the Milky Way. The Milky Way looks something like this cartoon. The sun is somewhere in the outskirts next to a spiral arm or on top of a spiral arm, as Catherine has been telling us. And we view the Milky Way through a projection. We view the sky as a two-dimensional sphere. So all of the photons that are coming at us at all different directions get projected on this two-dimensional manifold. And if I open up the sphere of the sky, this is what the galaxy looks like. There's a bright band that is the Milky Way in the middle. You're looking towards the galactic center at the center of the image, and there is the anticenter and the edges of the image. And so light from nearby and far away gets confused, and we end up with having constraints that are two-dimensional, but inherently they come from a three-dimensional field. The constraints that we've used to make the models that I showed you before on the galactic magnetic field look something like this. This is an image of the cosmic ray electron emission from our galaxy, and the overlay is the magnetic field lines. And this has been measured by the Planck mission. So the two-dimensional data that we have is not enough to be able to recover this missing third dimension along the line of sight. So we need new data and new methods to be able to recover this missing information. And that's exactly what my research has been about in the past couple of years. I'm trying to apply new methods on data that are coming online to try to create an accurate representation of the magnetic field of our galaxy in 3 dimensions. And so what I'll talk to you in the next part of my talk is a little bit more about how we're trying to solve this problem. So we know light is an electromagnetic wave, and we measure magnetic fields by the interaction of this electromagnetic wave with the magnetic field itself. And so light has 3 properties. It has an amplitude, which is the brightness. It has a wavelength, which is the color, and it has a polarization, which is the plane in which the E vector of the wave oscillates. And so natural light, like we see outside, is typically unpolarized, which means it has light rays that come at all different directions of polarization. Now, if you put sunglasses on that are polarized or insert some other polarizing filter, then you'll get, you'll convert this unpolarized light into polarized light. You'll get a preferred orientation of the oscillation of the E vector. And it turns out that space also carries its own polarizing sunglasses in the form of dust grains. So dust grains are funny things. If you look at them under a microscope, they're anything but spherical. And if you put particles like these that are charged and give them a kick and put them in a magnetic field, they'll tend to align with their short axis parallel to the magnetic field lines. And that's what the cartoon on the left is showing. Now, if you have this bulk medium that's dusty and all these grains are aligned, any starlight that's behind this medium is going to acquire a polarization with an E vector that's parallel to the magnetic field. And so you can use this to map out the magnetic field. And that's what people have been doing. But now what's changed in the past 3 years is that we have Gaia, this European Space Agency mission that's been measuring the distances to billions of stars by using parallaxes. So on the left, I'm showing you a field of stars with polarization vectors for each star overlaid. And what Gaia is giving us is that depth perception. We can now map for each of these vectors where in the sky the star that's producing the light exists. And so we can use this combined information to make maps of the magnetic field in a tomographic way. At a very simple level, if you have one dusty medium, one cloud, that is threaded by a magnetic field like the cartoon on the right, and you also have stars distributed along the distance axis, stars that are in front of this magnetic field are going to be unpolarized. Stars that are behind are going to acquire some linear polarization that tells you what the direction of the magnetic field is. And also you get a distance because you know which stars, after what distance you start to see polarization. And so you can use this very simple understanding to actually map out the nearby structures around the sun. And this is what we've started to do in a paper that was published in 2021. We took regions of the sky that were very bright in cosmic ray emission. On the left, you're seeing again the radio map of the cosmic ray electrons emitting. So in this pink circle that I've marked here, we're looking at 2 different methods of measuring the orientation of the magnetic field. The red vectors are showing you the magnetic field from this 2-dimensional cosmic ray emission map, the synchrotron map. And the yellow vectors are showing you the magnetic field measured from stars. And you can see that overall, the 2 methods agree. But what you get with Gaia is that you can find at which distance these 2 vector fields start to agree. And that gives you a distance to the structure. And just to give you a little bit more detail, I'm not going to show this to the biologists, if you're wondering. So what we're finding for this region, that's called the North Polar Spur, is that if you look at the polarization angle of stars, which is theta star, versus the inferred magnetic field orientation of the cosmic ray emission, after some distance, you start to see overall these angle differences align. So we know that this emitting structure is at about 100 parsecs from the sun, very nearby, in our face. So, and the bottom panel just shows you that there's a corresponding jump in the extinction as a function of distance. And this has also been seen with data that Catherine and Caltech, who's a grad student here, have shown. So that all agrees. So next up, let's try to think bigger. Let's try to go deeper in distance. How can we map further away clouds than just 100 parsecs in front of our face? Well, the idea is if you have, let's say, two clouds, take it step by step, two clouds along the line of sight, there will be stars distributed in three groups. There will be stars that are foreground to both clouds, stars that are in between, and those will be only polarized due to the effect of the nearby cloud. There will be stars further out, which are polarized additionally due to the effect of the faraway cloud. So as a very simple picture, you can imagine that the polarization parameters, that's what we expect, will be piecewise constant functions of the distance. And so you can model this with the data that you have, well, with the data that you take from a telescope. So back in 2018, I used a telescope we have in Greece to measure the polarization of 100 stars in each of these two very small beams on the sky. And by using these data, we were starting to probe stellar distances out into the inner halo at 6 kilo light years or 3 kiloparsecs. And the end result was that we were able to measure the magnetic field in a further away cloud. So on the left here, you're seeing the distribution of gas, neutral gas, for the nearby cloud. And on the right is the same thing for the faraway cloud. And the vectors that I've drawn are the magnetic field orientation that we measure for the nearby cloud and for the faraway cloud separately. And now this cloud that we're measuring, the faraway cloud, is just at the interface between the halo and the disk at about the scale height of the atomic layer. So we want to do this for most of the sky, right? We want to be able to map out distant clouds by using this method. But in order to use it, you really need lots and lots of stars. And it turns out that there aren't that many stars with stellar polarization, unfortunately. This is a map that shows you the number of stars with measured polarization in each pixel of the sky. The gray is 0 stars with stellar polarization measurements. The black shows you 1 star with the measurement, and the white rare pixels have 10 or more stellar measurements. And so in order to do this exercise of tomographically mapping the magnetic field, you need hundreds of stars. And in order to get this kind of information, you need a survey. And that's exactly what we're doing with colleagues here at Caltech, including Ram right there in the center, who's building our instrument. Sorry, Ram. So PASIFI is the optical polarization survey that we're starting to measure this number of lots of stars that we need. PASIFI is the largest optical polarization survey there has ever been. And it's a collaboration between the University of Crete in Greece, led by PI Kostas, Caltech over here, University of Oslo, IUCA in India, and the South African Astronomical Observatory. The goal for PASIFI's first 5 years is to cover these dark gray regions that I've marked, about half of the sky at high latitudes. And by doing this, we'll be measuring millions of stars for the first time in optical polarization. And to give you a sense of what this means for the field, I've compiled the plot that shows you the number of stars with polarization measurements that we've had over the years, ever since the first detection of stellar polarization back in '47. So about in the 2000s, Carl Heilis compiled a list of all the available stellar polarization data, and those were about 9,000. Now in 2021, I led a group of students and postdocs to go through the literature and find all the polarization data that have been published. And we compiled a catalog that has 30,000 stars. And just in the next 5 years, PASIFI is going to give us 10 to the 7 stars. So that's 3 orders of magnitude increase in the amount of data that we have to map the magnetic field of the galaxy. And in order to make sense of all of this data, we need to up our game in terms of methodologies. And that's where machine learning and other approaches come in. So machine learning, as many of you know, because you're running surveys, is essential to running big surveys. It's essential from the data collection stage to the data processing to the astronomical analysis and to the final end product, which for us is the magnetic field map. And so I'm going to show you briefly two use cases of how we're using machine learning to better explore our data and the end product, which is the magnetic field mapping. So the first use case is related to data cleaning. Now, back in 2015, I was looking at images from the telescope in Greece with the polarimeter. And if you've never seen an image from the telescope, it's not a faithful representation of the sky. It has things that you have to correct for, like earthly dust, or satellite trails, or atmospheric conditions that vary. In this particular case, what I was trying to find was the reason why some of the stellar polarization measurements were way off. And one of the reasons was that there was residual dust in the instrument that was blocking some of the light from the telescope. And for this instrument, for the experts in the room, we can't flap field. I can explain later why. So the trick was to find where these stars were falling on the CCD so that we got the, we could get rid of them basically. So any star that falls on the shadow cast by the dust grain has to be thrown out. And I found that if you explore the parameter space, you only need about 6 different features to be able to reliably clean the data from this artifact. And of course, this approach is good if you have hundreds of images and a grad student. If you have millions of images, that's a little bit of a problem. And so instead, what we're doing is using convolutional neural networks. Now, we had a very smart student, Drew Pranchpai, come visit us here at Caltech back in 2019, just before the pandemic. And Drew constructed a convolutional neural network that was able to classify images of stars versus images of artifacts. And the particular artifact that Drew was trying to clean actually looks like a little bit like a UFO. And in reality, it's just a reflection off of the detector from a different part of the, a bright star fell somewhere in the wrong place. And so Drew's convolutional neural network is able to classify with great fidelity stars from artifacts. And using a neural network is great for a classification problem. It's also very efficient because once you train the neural network, then you can just use it forever. And so this was one of the use cases that we have. The second use case is machine learning for dimensionality reduction. Now, in a paper that was published this year, Giuseppe Puglisi, who was a postdoc at Berkeley, led this effort to use unsupervised machine learning to identify clusters on the sky that had similar properties, specifically similar properties of the dust emission. And what Giuseppe did was to work with a mathematician and with other folks like me to figure out how do you cluster on a 2-dimensional manifold that is a sphere. And so this paper for the first time shows how you can do that. And it also shows that you can identify hundreds of clusters on the sky, which is what the image is showing you. And instead of having to work with, for example, 10 to the 5 sky pixels, you can only work with hundreds of subregions where you expect properties of the interstellar medium, the magnetic field, to be sort of similar. And so these were 2 use cases. We're exploring other pathways as well, but to not bore you too much, let's look a little bit into the future. So the future is bright for the field of cosmic magnetism. There's an array of facilities that are producing data as we speak. There's NASA's SOFIA, there's the Very Large Array, there is CHIME and other telescopes, as you all know, like the DSA, that are measuring magnetic fields, in a sense, over the nearby universe. And so this influx of new data has been matched with an influx of the ability of theory and simulations to predict very precisely what the emission, let's say, from cosmic rays in galaxies should be. And this is an effort that many people in Phil's group are doing, including Sam over there, myself, and Irina Butsky. And we're trying to make precise predictions of what magnetic fields and the cosmic rays that follow them should look like with telescopes like the ones on the left. And so in the next decade or so, all of these efforts for measuring magnetic fields are going to culminate with the Square Kilometer Array, which is a huge telescope that's being built and which will measure the magnetic fields of galaxies far, far away, much further than we've ever seen. This is going to bring big data like we've never seen before. This is, I think the projected rates are 5 terabits per second for the raw data stream, and this is going to be a telescope that runs around the clock. And so to give you an idea of how I see the path forward for where my science is going, first off, we'll be creating this stellar polarization survey that's going to give us an upsurge in the amount of stars available for magnetic field mapping. We're going to use this data to make the first 3D map of the magnetic field. And this will inform our models for cosmic rays and how they transport, how they propagate through the galaxy and into the surrounding medium. And we can use all of this new knowledge to better constrain magnetic fields further out into the universe. And so to sum up, in order to have a complete view of the universe, we really need to understand the only tracer that we have, which is the normal matter. And I've shown you, I think, that the main uncertainties in understanding normal matter come from how magnetic fields and cosmic rays, well, some of the main uncertainties come from how magnetic fields and cosmic rays interact within galaxies and their surroundings. And our knowledge of these two components has been a bit fuzzy over the years, but now we're having new data and new methods that are going to give us the ability to have a 3D view into the properties of the magnetic field. And so to sum up, I think research on magnetism in the universe is a blossoming field. I really think there's a lot of room for discovery and exciting collaborations to be made. And so that's where I'll end my talk. Thank you very much for listening. You've gained 20 minutes of your time.
Yes, we have plenty of time for questions. So folks online, you can raise your hand. And this time the speaker is working, so you should be able to ask them directly. Okay, let's start with the audience in person. You want to?
Yep.
So I think that would measure the polarization both on optical and radio.
Can you speak louder?
Oh, so it seems that we can measure the polarization both on optical and radio.
Yep.
And what's better, which wavelength works better, and why would we need two wavelengths?
So
Gina, can you repeat the question?
So the question is, you can measure the polarization both in the radio and the optical. Why do you need both? Is one better than the other? Is that the question? So radio is emission, which means it's only a two-dimensional information. The stars are absorption, which means you also have distance information. And so you can use the stars to know, as a function of distance, what the magnetic field is doing. Whereas in radio, you're collapsing, you're integrating over the entire line of sight. So you get one vector over the entire line of sight. Does that make sense?
In the radio, we are also observing stars.
So this is diffuse emission of the galaxy from, not from discrete sources, but the kind of information that we use to constrain magnetic field maps is the emission from the interstellar medium and the cosmic rays that are in it. And this is the diffuse gas, not individual sources. But you're right that there are, if you're doing Faraday rotation, for example, so measuring the polarization shift with frequency for, say, a quasar that's behind some intergalactic medium, then yes, you have some, that's a feature that can give you distance information. But for the galaxy's magnetic field, we're primarily using this kind of information, We also have pulsars, but that's a different story. That's the sampling of pulsars is not great, but I think I'm going too much into the detail. Yeah.
Okay, Dylan was next.
So with 10 to 7 stars expected, do you think that limits in parallax accuracy from binary expected are going to start to vanish?
Yeah, we will.
Sorry, can you repeat it again?
Sorry, yes. So with 10 to the 7 stars measured in polarization, do you think that parallax uncertainties are going to be an important thing to consider? And so I think yes, once you go further than, say, a radius of 1 kiloparsec or so, you need to start worrying about the parallax. And the tools that we're developing to do the magnetic field mapping are taking into account the uncertainties in the parallax. And so that's incorporated in the likelihood of the Bayesian approach we have. So I think there will be, resolution in distance space will not be as good as for the faraway clouds versus the nearby clouds. It's still a start.
Okay, we've got a couple more in the audience I'm going to come back to, but first I want to take some questions from folks online. Shri, are you ready?
Yeah, so Gina, you mainly talked of polarization, which is to do with the magnetic field. But as you started off and you're concluding, there's the other part, which is the cosmic rays. Do you have any ideas on how to address the cosmic ray distribution in the galaxy? Because the ones that matter for what you're interested are the low energy ones. And they're almost impossible to measure other than directly in the solar neighborhood.
Yeah, so there are many things you can do. What I started to sort of mention is that if you have a good model for the magnetic field of the galaxy, you can put that into models for the propagation of cosmic rays. And that will improve you'll get rid of all the systematic uncertainties associated with the magnetic field models that we have already. So in order to figure out how cosmic rays diffuse in the galaxy, I should say, we do use models like a model that's called GalProp that takes into account the distribution of the magnetic field in the galaxy and solves for how all the cosmic rays interact and what the scattering rates are. And so as a first step, you'll make an improvement just because you have a better model of the magnetic field. And as a later step, you have simulations like Phil is making, and you can put by hand different scattering rates or different functions of how the scattering rate of the cosmic rays mixes with different magnetic field properties. And you can make detailed predictions for what that's going to do in galaxy properties. And that's another avenue that we can also talk about and we're pursuing. Did that answer your question at all?
Yeah. By nature, I'm very skeptical of all the simulations and stuff like that. I prefer something which is robust and reliable. So I don't know the solution, but it does seem that the magnetic field strength topology is being addressed, which is a lot better than having nothing. So, but I think the cosmic rays, in my opinion, are an open, unanswered, and perhaps within 5 years after you finish your survey will be the one thing we don't know much.
I agree.
Okay, Sterl, are you ready?
Yeah, thanks, Gina. So you mentioned, of course, measuring the magnetic fields from the orientation of the dust grains, but of course that requires knowing which direction the dust grains are oriented, and there's a 70-year history of arguments about paramagnetic, superparamagnetic, ferromagnetic grains, oblate versus prolate grains, fractal messes, radiative torques, thermal torques, Davis Greenstein Gold, Lazarian, and so on models. So do you see any way of separating? I mean, the first question is whether the grains are aligned perpendicular or parallel to the magnetic field, or whether they care about the radiation anisotropy and are aligned with the radiation gradients in some cases.
Yep.
So do you see any way of settling these sorts of questions?
Yeah, so I don't know if you know the review by B.G. Anderson in 2015, Lazarian was in as well, and they present the state of the art in comparing all these different models, especially the radiative torques, with observations. And what they find is that the dominant mechanism in the ISM has to be, the dust grains are basically aligned because of torques with photons. Photons hit them, and these cause the alignment. And this alignment is in the sense that I showed. So the long axis of the grain is perpendicular to the magnetic field. And only in very specific situations in the interstellar medium, specifically when you're close to a very bright star, and that this has been detected, you start to get a different alignment. Or you can have this also in protoplanetary disks, because basically you're starting to align with the radiation field and not the magnetic field. But in general, for the diffuse ISM and the stuff that I've been talking about, it's this radiative alignment of the grains that results in this kind of alignment that dominates, and we're pretty sure about that. And also gold that you mentioned, the gold mechanism is basically arises if you have dust grains that are in motion with the gas and there's a drag, and that gives you the entirely wrong sense of the orientation. You can compare this to the synchrotron emission of other galaxies. This has been shown, for decades now, and that's how they know that these mechanical alignment mechanisms don't work. But there is things we can do to constrain dust models and dust alignment models. If you have this sort of data set, you can, like B.G. Anderson is sort of using nearby stars in the local bubble to see if he can find changes in the alignment efficiency, for example. But you were going to say?
Well, I was just curious, the question of whether it's parallel or perpendicular does depend on the grain shapes and the grain compositions. I mean, there's been a long question of whether there were any iron atoms in them and whether they're super paramagnetic and so on. So
that's a good point. Yeah, so we think that the silicate grains are the ones that are aligned, the carbonaceous grains are not. And there's a possibility for magnetic inclusions, and that would just change the efficiency of the alignment, but it wouldn't change, as far as I know, it wouldn't change the sense of the alignment.
And oblate versus prolate versus fractal, you think makes no difference in the polarization?
It might make a difference in the amount of polarization. We can talk more about this later, but it won't make a difference in the angle.
Okay, I'm going to move on. We have a couple of questions from the audience still.
Yeah, so following up on the question about the direct galaxies, I'm just curious how far in distance you'll be sensitive to the magnetic field, and then how you think the spatial resolution of your magnetic field now will vary as a function of distance.
Right. So the question was, again, on the question of parallaxes, do you know what the where you lose sensitivity, at what distance you lose sensitivity for measuring the magnetic field?
Yeah.
Okay.
And then how the spatial resolution varies.
And how the spatial resolution varies as a function of distance. So I think that the dominant limitation, because we're looking straight up and straight down, is going to be the absence of dust. And so we're just going to add about where the atomic layer ends, 1 kiloparsec-ish, 2 maybe. That's going to be our limit, because there's not much dust further out. We can try to do stacking experiments, but I think the parallaxes are going to be the least of our troubles. If you want to do this for the galactic plane and do a different survey, then yes, parallax is important.
Okay, next up, Viraj.
I was just curious about what were the selection criteria used to select the 10 to the 7 stars that we plan to observe?
It is a survey. So the selection criterion is basically the exposure time that you set. And our limiting magnitude is going to be 15 in the R band, 15 magnitudes in the R band. So this is a wide field instrument, right? It's going to be half a degree by half a degree is the field of view. And we're just scanning all throughout the highlighted sky.
Are you worried about intrinsically polarized stars?
Very much. We're worried about intrinsically polarized stars. We need to find ways of efficiently cleaning the data from these. And these will be interesting for folks like you or other folks that are studying transient events, for example, or AGN. But yeah, we're working with machine learning or combining the information that we have from polarization with, say, time variability surveys. That's going to be a big thing to clean these up, because they're not telling us about the magnetic field of the ISM at least.
All right, I think this will be the last question, Dylan.
I've got 2 questions. So following up to Sterl's question, if composition is important, do you think you can break the differences using cosmology?
Can you tell me more?
As in, can you tell what the composition of the dust is based on different levels of absorption in different bands, for example?
I think,
Will you repeat it?
yes. So the question is, can you use infrared spectroscopy to tell something about the composition of the grains? And I think this is one of the ways in which they found out the composition of the grains. There's one of these big features that the silicates have and the carbonations ones don't, when you compare the total spectrum compared to the polarization spectrum. That was one of the ways that they found that carbonation grains are not polarizing. But there are other things that you can do, and I can point you to papers if you're interested.
My other question was, do you think that it'll be possible to trace the directions that, or trace cosmic rays coming from like recent supernova remnants that are nearby? Or do the directions get scrambled so much by the magnetic field that you never be able to tell?
I don't know. The question was if you can trace cosmic rays from individual supernova remnants.
Yeah.
So you can use the change in spectrum of the spectral index of the synchrotron, for example. You get a different slope when you look in from the emission within the supernova remnant, but I'm not sure if our magnetic field map is going to be, I'm not sure.
All right. Well, thank you again, everybody, for coming. Thank you, Gina, for an excellent talk. Thank her again. We will see you all next week.